Okay, we've talked about land-based transport of different types, cars, trains, planes, walking, cycling. Now let's talk about water and air transport. If we look at these figures, we can see that the worst form of transport in terms of energy per distance for a person is actually an ocean liner. And aircraft are pretty bad as well. So why does anybody use them? Let's look at water travel first. Now the figures I showed there were calculated using consumption fuel for the QE2, a liner now decommissioned and turned into a hotel. What dominates the energy consumption of a ship? Well, the ship has to have a considerable amount of area under the water's surface because it's the buoyancy of that area that keeps the whole thing from sinking. And that space has to be pushed through water. There's going to be a drag force. And because water is about 1,000 times more dense than air, that's going to be a big drag force. The underwater parts of ships are very streamlined, but even so, that density really kills you. So that means speeds need to be low. That's why ocean liners might go at 30 or 40 kilometers an hour, so 3 or 4 times slower than a car and much slower than an aeroplane. It's because you're battling the density of that water. The energy per person on liners and cruise ships is bad, but that's because they don't carry very many people considering how big they are. I mean, look at the size of this thing, and it carried typically, when it was full, about 1,000 passengers and another 1,000 crew. If you packed people into one of these things like you do on an aeroplane, you could probably fit 10,000 or 20,000 people on there, in which case the energy per person per 100 kilometers would look really good. But because they're so slow, people are not going to sit in like economy class seats for a week's travel across the Atlantic, so you need more space so people can sit around, have dinner, go to the bar, have a room to sleep in and so on. So that's why you need so much space per person, and that's why they're so expensive. But there have been times historically, for example, the ship was commandeered during the Falklands War to be as a cruise ship, as a troop ship, when they could pack 5,000 people on, and then the energy per person is actually comparable to planes, not so bad anymore. But the main use of ships is cargo transport. There are far more of them than there are passenger ships. Maybe a container ship like this one over here, or bulk transporters, so things like oil or coal, or specialized car carriers. And these dominate the CO2 emissions and the number of ships out there. The reason is that a shipping container doesn't matter if it takes a week to get somewhere as opposed to a few days. It doesn't need any more space, and so transporting large amounts of weights not very fast, so the drag is low. These can be very efficient forms of transport. Many of these container ships are very, very large, as you can see. But they typically burn bunker fuel. Bunker fuel is the thickest, most toxic form of oil to come out of refineries. It has the same sort of 45 to 50 megajoules per kilogram energy of any other fuel, but it produces a lot of toxic pollution from it. And a really big modern container ship like this one here, this is like a 20,000 TEU container ship, they burn about 400 tons of bunker fuel every day. 400 tons. So that's telling you right away that electrifying these is going to be very hard. Remember that each ton of bunker fuel would need to be replaced with about 50 tons of lithium-ion batteries. So if you have 400 tons a day, a 2-week trip, that means you need 250,000 tons of lithium-ion batteries. So first of all, that's going to run the world's supply of lithium-ion batteries out, to open a whole new lithium mine just for one of these ships. But also, the whole displacement of the ship is only about 250,000 tons. It would be all battery. There'd be no weight for anything else. So in fact, taking these really big ships, or any sort of container ship, and electrifying them with lithium-ion batteries is not going to be a good idea. There may be other battery technologies. Weight is less of an issue for these things, but it's going to be very challenging. So people are talking about decarbonising ocean transport. In the short term, the idea is to take the existing ships and somehow gain energy efficiency, make them 10-20% more energy efficient. And there are various ways you can do that. The most obvious way, because they're limited by drag, is to go slower. Going slower means you need your v squared less force, v cubed less power, but you'll take longer time. So when you factor it all in, the total energy consumption for a given journey is going to be inversely proportional to the velocity. So if you bring the velocity down by 20%, the amount of fuel needed for the same trip is going to be about 20% less. Which does mean you're going to need more ships, because they're going to take longer, so you need to have more of them to shuttle backwards and forwards to transport the same amount of cargo. So it's going to be expensive. Another idea that's getting a lot of traction at the moment is putting sails, going back to the old-fashioned way of sailing ships. No one's suggesting you actually go back to a fully sailed ship. Those needed crews of hundreds of people to climb up the rigging and rig the sails. You need something that's going to be far more automated to make it cheaper. And there are experimentations. You can have mount a sail like this on your ship. It's not going to propel the whole ship, but it might save a few percent in terms of your energy. And a few percent of your 400 tons is a lot of fuel. Another thing that might be even easier, if you've got the wind in the right direction, is to deploy something like this, a type of kite or airfoil. And again, the idea is that both these things would be heavily automated. There'd be computers adjusting where it goes, so it's not going to be too much work for the crew. You don't need to have a huge crew to climb the riggings. So this will help. The amount by which it helps may be about 10%, and that's worth having, but it's not going to really solve the problem. So for full decarbonisation, to totally get rid of the burning of fossil fuels, you're probably going to need some form of hydrocarbon energy storage, some zero-emission fuel. And so this could be biofuels, which have the same problem that you need a lot of land to grow them, because of the low efficiency of photosynthesis. Or it could perhaps be green hydrogen. We'll talk about hydrogen later, but the idea is you use solar power to split water into oxygen and hydrogen, then you store the hydrogen somehow and then burn it, producing water vapour and powering your ship. So it's probably going to be some combination of these are how we decarbonise ocean travel.